when we list out the prime factors of perfect squares, what ends up happening is when we factor this, so they can do this in a number of different ways. Here I've done a factor tree, but when we do the prime factors, I end up with 2 times 2 times 3 times 3 times 2 times 2 times 3 times 3. And what ends up happening with perfect squares is we can always group factors into common groups of pairs. Okay, so here we have a pair of 2's, a pair of 3's, and anytime we have perfect squares, this is always going to be the case. Okay, we can group them into pairs. So here, when we have 144, okay, so when I factor 144, so I'm going to divide by 2, so I get 72, divide by 2, 36, divide by 3, I get 12, divide by 2, I get 6, divide by 2, I get 3. Okay, so here I end up with 2 times 2 times 2 times 2 times 3 times 3. So again, this perfect square, all the prime factors can be grouped into pairs. Okay, pair of 2's, pair of 2's, a pair of 3's. For 196, same thing. Okay, we're going to end up with, let's do 6 times, that's going to be 6 times 12. No, that's not 6 times 12. 6 times 33. No, that's going to be 6 times 180. Oh, it's not going to be 6. Let's do 2 times 98. 2 times 49. 7 times 7. Okay, so when we write out the prime factors of these, again, you can see that the prime factors, again, can be grouped into a pair of 2's, a pair of 7's. Okay, 1024, when we prime factorize that, we end up with 2 times 5, 12. We end up with 2 times 2, 56. Okay, so that's 2, 5, 6. We end up with 2 times 128. Okay, we end up with 2 times 64. Here we end up with 8 times 8. Okay, 4 times 2, 4 times 2, and then the 4 becomes 2 and 2, 2 and 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 2's. So 2 times 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 2. I think that's 10. Okay, and we can group those prime factors into a pair of 2's, a pair of 2's, a pair of 2's, a pair of 2's, and nothing left over. That means this must be a perfect square. Okay, so when we have perfect squares, if we look at the prime factors, we can tell if something is a perfect square if all the prime factors can be grouped into pairs and with none left over. That indicates then that that must be a perfect square number. Okay, so here we have the squares for A and B, so 36 squares. So what you're being asked for is find the side length. To go from area to side length, we square root. Okay, the side length that gives us 36 squares is going to be 6 centimeters. Okay, and we can actually draw in all 36 squares too, if you really want. Okay, so we have 6 this way, and we have 6 this way, and you can count all 36 squares in there. Okay, so then we could do the same for 144. I'm not going to draw on the squares, but to go from area to side length, we square root. Make sure your units are consistent. Okay, and then the 144 squares, centimeter squares, goes in the middle there. Okay, and the last part of this says to find the side length of squares for large numbers 196 and 1024. How do the prime factors help? Well, the prime factors of perfect squares can be grouped into pairs. So prime factors of perfect squares, perfect square numbers, can be grouped into pairs. With no leftovers. Okay, just write that a little bit nicer. Perfect square numbers Okay, so if we have prime factors, the prime factorization, they can all be grouped into pairs, and you should have no factors left over, and that means that you're dealing with a perfect square number.